Hi guys, this is Mohammad Anikuzaman, and today I'll present our work on Oracle-free reinforcement learning in mean field games along a single sample path. So this is just an outline of the presentation. I will start by motivating the problem. This will be followed by the literature review. Then I will formalize the n-player Markov games, which will be followed by the Markov mean field games. For Markov mean field games, I will first define the mean field equilibrium of the mean field game and its accompanying epsilon Nash guarantee. Then I will introduce the concept of Boltzmann mean field equilibrium. Having defined the equilibrium concepts in the mean field game, I will move to the Oracle-free reinforcement learning algorithm to compute these equilibria. To compute this equilibria, we will need episodic two-timescale learning, which will help us overcome some of the obstacles in the learning algorithm. Then I'll present the finite sample bounds of the algorithm. And finally, I'll present the numerical analysis of the algorithm. So first, we look at the question of why reinforcement learning is important for mean field games. As you all know, there have been tremendous advances in reinforcement learning for applications such as robotics, autonomous driving, and games such as chess and poker. Most real-world scenarios involve multiple learning agents which are in competition. This is a game theoretic scenario, and some examples of this scenario are traffic networks, portfolio management, and spread of epidemics. Hence, reinforcement learning for games is a very important concept. But there is a scalability problem in game theory. As the number of players and increasing, solving a game gets harder, and even when the model parameters are known. So it's very hard if we are operating in an RL setting where the model parameters are unknown. The solution to this is the mean field game paradigm, where the number of agents goes to infinity. And under this setting, the solving the game is easier, and also the solution to the mean field game is valuable for the finite population game. But most works that work in reinforcement learning for mean field games assume access to a large population simulator or a mean field oracle. An example of a mean field oracle is in financial applications, it can be something like a market simulator. Now, having access to this sort of a market simulator or a mean field oracle is very restrictive. So in this work, we try to get rid of this assumption of mean field oracle. Before moving on to the algorithm, we will just briefly introduce the literature in this area. The first two works of Eli et al. And Cui et al. Are some of the early works in reinforcement learning for mean field games. They assume access to an oracle, but also they do not provide finite sample bounds. The next three works are Fu et al., Gu et al., and Anatarchi et al., which also assume access to a mean field oracle, but they do provide finite sample bounds under a linear quadratic assumption, a covering time assumption, and an ergodic Markov chain assumption, respectively. Then the work of Shi et al. Was the first work that detailed a single loop algorithm to find the mean field equilibrium of the mean field game. It provides finite sample bounds under a covering time assumption. The recent work of Anguilli et al. Provides the first work which does not assume access to an oracle and provides an RL algorithm, but does not provide finite sample bounds for the algorithm. The recent work of Yardim et al. Also works with an oracle-free algorithm and provide a finite sample bounds under an ergodic Markov chain assumption. The ergodic Markov chain assumption is a bit restrictive because it assumes that the Markov chain of the generic agent is ergodic under any given policy. This may not be satisfied in examples such as congestion game, where if you have a policy that the agent always moves to the neighboring cell, then that might lead to a periodic Markov chain, which will nullify the ergodic Markov chain assumption. So in this work, we provide an oracle-free algorithm which works on a single sample path of the generic agent, and also we provide finite sample bounds under something called a communicating MDP assumption, which is much more general than an ergodic Markov chain assumption or a covering time assumption. So we start with an n-player game where an agent I in a set of n is the state of the agent I is denoted by SIT, the action by AIT, and the dynamics of the agent are affected by the state, its action, and something called the empirical distribution, which is just the distribution of all the n agents over the state space. The reward of the agent is also affected by the state of the agent, the action, and also the empirical distribution. And the agent wants to maximize its discounted infinite horizon reward. The Nash equilibrium of such a problem is hard to compute, so instead we go to the Markov mean field game formalism, where the number of agents goes to infinity. In this setting, we deal with a generic agent whose state is ST and action is AT, and its dynamics are affected by the state, the action, and the mean field distribution, mu. Here we assume that the mean field is stationary because non-stationary mean field distribution will be infinite dimensional and be very hard to solve. The agent's reward at time t is dependent on the state, the action, and the mean field, and the agent wants to actually maximize the discounted reward. Now we define the mean field equilibrium of such a mean field game. To define the equilibrium, we define two operators. The first operator is the optimality operator, which outputs the optimal policy of the mean of the game given the mean field mu. And the second operator is the consistency operator, which outputs the mean field mu, which is consistent with the policy pi and mean field mu. Having defined these two operators, we define the mean field equilibrium of the mean field game, which is a tuple denoted by tilde pi and tilde mu, such that pi tilde is optimal with respect to mu tilde, and mu tilde is consistent with respect to pi tilde and mu tilde. Mean field equilibrium is shown to be epsilon Nash for a finite player game, and epsilon goes to 0 as the number of agents goes to infinity. But the problem is that the composite operator gamma 2, gamma 1 is non-contractive. So instead we replace the optimality operator with an approximate optimality operator, which implies a softmax of the Q function. And the softmax is defined here. Under this varied definition, we now define the Boltzmann mean field equilibrium of the mean field game, which is a pair pi star and mu star, such that pi star is approximately optimal with respect to mu star, and mu star is consistent with respect to pi star and mu star. As lambda goes to infinity, the approximate optimality operator approaches the optimality operator, and hence the Boltzmann mean field equilibrium approaches the mean field equilibrium. But there's a problem. The composite operator may not be contractive for small lambda. Hence, there's a trade-off where we choose lambda large enough such that the composite operator is contractive, and also we have a closeness of these two equilibria. So now we move to the oracle-free RL for Markov mean field games. So can we devise a provable oracle-free algorithm along a single sample path? The answer is yes, and we do it using construction of data-driven versions of the optimality operator and the consistency operator. Using the simple sample path of the generic agent, we update the mean field and control policy concurrently, and we devise episodic learning rates for the convergence. So first we take a look at the consistency operator. To approximate the consistency operator, we need to estimate the transition probability matrix P under a given policy pi and mean field mu. And to approximate the optimality operator, we need to estimate the Q value of under a mean field mu. There is a problem though, because of concurrent update and the Markov chain of the genetic agent is time varying. And this is ameliorated by using an episodic learning rate such that inside the episode, the learning rates are fast decreasing. They're summable, which leads to a slowly time varying Markov chain within the episode and allows for good approximation of the operator. The two timescale learning rate allows for a policy update which is faster than the mean field, and it gives us the mean field equilibrium as shown later on. Now we go to the oracle-free RL algorithm. We start with the state S, a policy pi, and a mean field mu. And this algorithm goes on for k episodes, and each episode has capital T time steps. The mean field is updated using the P transition matrix estimate. The policy pi is updated using the Q function estimate, and we generate a new state using pi the policy. The transition probability is estimated using this equation, and Q learning is updated using this equation, which is standard. We note that this is still a single sample path because we don't have any initializations of the genetic agent's Markov chain. And the output is the average of the policies and the mean fields. Now we present the finite sample bounds under the communicating MDP assumption, which just states that the MDP of the genetic agent under a mean field inside the epsilon net is communicating, meaning that there exists a path from any state to any other state in finitely many actions. This assumption generalizes assumptions in literature and results in sufficient exploration of the state and action space. Under Lipschitzness of P and R and communicating MDP assumption, we ensure good estimation of the transition probability and the Q learning. This is the proof of first lemma relies on the Friedman's inequality, and in the second lemma we decompose the error into several bounds and deal with each of them separately. Finally, we reach our main result of the paper, which says that the output of the algorithm is close enough to the Boltzmann mean field equilibrium, given that the number of episodes k is large enough, the inter-episode learning rate is large enough, and also the transition probability estimation and the Q learning estimation is good enough. The convergence of pi is proven due to faster learning rate, slowly time-varying Markov chain, and good estimation of Q function. Convergence of mean field is proven due to convergence of pi, slowly time-varying Markov chain, and good estimate of the P matrix. Now we present a numerical analysis on a congestion game. First, we show that the inter-episode learning is good, meaning that inside the episode, the Q function and the transition probability estimation achieve the estimated results. And also the mean field and outside the episode, due to the good estimation of the Q function and the transition probability estimation, the mean field and the policy converge to their correct answers. Finally, we also simulate this algorithm for a weakly communicating MDP, where the communicating MDP assumption is not satisfied. Hence, we cannot have any theoretical results for this setting, but actually empirically we show that the estimation still works and the mean field and the policy approach the correct answers. Thank you for listening to the talk.